guess what we're doing third period today? Titrating. And that's, guess what we're going to do on Thursday? Titrate. And then guess what we're going to do on Monday?
Explosions.
Titrate. You guys understand this, right? For the rest, literally for the rest of the year, we're just titrating every day in lab. It's kind of what we do. So guys, this is where we are at so that we know where we're going. So up until now, what we did is we defined a working understanding of acids and bases through the lens of Arrhenius and Bronsted-Lowry. We said, and if you want to look in your notes just to make connections, it all should be there. Guys, we talked about the idea that Arrhenius defined acids and bases in terms of what they do to water. Acids give away hydrogens to water, that makes hydronium. Bases give hydroxide to water, that makes bases. Then we added the Bronsted-Lowry definition, which is less about, still can be about, but is less about what they do to water and more about what they do to each other. So acids give away protons, bases take them in. Then, guys, we talked a little bit about the idea, the interesting, I think, idea of what is it that makes acids and bases strong and weak. I need to let my screen come to life. Come on. There we go. And so, guys, we talked about this interesting idea that HCl reacts into water, and when it does, it forms hydronium ion, and it forms chloride ion. Oh, my H has no gut. There we go. And then, guys, we talked about conjugate acids and bases. So if I tell, well, you should be able to do all of this. Guys, do you need more support on acids, bases, and conjugates? You're okay? So this is my acid. That makes water a base. And then, guys, the easiest way to do this is to find your conjugate base. Go to the acid, take away a hydrogen. This is your conjugate base. Hydronium ion is your conjugate acid. Questions about that? You guys good? Now this. What do we know about the basic strength of chloride ion? It is, let's just say worthless. It's worthless, of negligible strength. How do we know that? Because, guys, if this had any ability to function as a base, it would. And it would steal one of these hydrogens back from hydronium, driving the reaction in the other direction, and therefore reaching equilibrium. But we know that doesn't happen. How do we know? Because this is one of the strong acids that you guys invested most of the weekend in rememorizing, right? Because you know you need to know all the strong acids. Don't nod your head, you're lying, you don't even look at them. But guys, understand you need to know the strong acids, right? So what can we then say about the conjugate bases of all the strong acids? They're all worthless. Let that rattle in your head. Guys, all of the conjugate bases of the 7 strong acids, all are bases of negligible strength. What do we need to talk about before we move forward?
Are there really bases then?
So that's an interesting question. I mean, if we define a base as something that can take in protons, then no. They don't function as a base. But in the context of acid-base chemistry, we still think of them as functioning as the conjugate base. They just can't. And it's funny, you can tell my wheels are turning. There's another example of something like this that we're going to get into down the road. I don't even want to touch on it yet. But, okay. So guys, one last thing that we need to do, and that is simply define the word, we've done it before, but let's be sure. Guys, in chemistry, what does strong mean? Ionizes completely. And so guys, we talked about this idea. Aluminum hydroxide is a really, really, really good base. It's an amazing base. It's just not a strong base. Why? Doesn't dissolve in water. So guys, that's an important idea. Strong means completely ionizes in water. So let's remind ourselves which are the strong bases. Group 1 and heavy group 2 hydroxides. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium, calcium hydroxide, CaOH2, strontium hydroxide, SrOH2, and then barium hydroxide, OH2. Guys, those are the only bases that we consider to be strong bases. Not because there aren't others that are very effective bases, it's because those other bases like aluminum hydroxide just don't dissolve in water. Is that okay? Okay, so guys, I'm going to sit down. I'm going to take a breath for a moment. I need you to be thinking about questions. Guys, what we just talked about is where you should be now. What questions do you have? What do we need to talk about? Yeah.
So since I don't know, since weak acids are always, when you put them in water, they're in an equilibrium reaction, right? Because
I'm always scared of always, but okay. There you go. Yes.
So then, why wouldn't adding more water increase the amount of hydronium, making it more have more?
Yeah, that's an interesting question. Let's play with it. So you need to get used to this nomenclature. Do you guys know what nomenclature means? Way of writing, way of identifying something. You need to get used to this nomenclature. These are called HX acids. So it could be chloride, it could be acetate, something sits in that place of X. So if we've got a weak acid, this is what it does. Let's include the water. Because you're talking about water, let's include the water. So it goes X minus and then hydronium ion, right? Okay, so if we've got something at equilibrium, actually, as I think about this through Le Chatelier's principle, your question gets even better. What I heard you say initially is, if we add more water, why doesn't that protonate more of this acid, right? Make more hydronium. Yeah, so protonate more of this acid, making more hydronium. Was that your question? And I would even confuse the question even more by saying, doesn't Le Chatelier's principle say that if we increase water, it increases the concentration of hydronium, right? An even stronger argument for your point. The answer is that it does not. And the reason is because of the... What's a good word here? The reason that it doesn't is because of the very small extent to which these weak acids actually protonate. So the idea is that compared to all the water that these acids are being dumped into, there's relatively so little of this that adding more water doesn't give these more of an opportunity to break apart, because compared to the amount of water that's there, there's so much water present that if more of these guys wanted to break apart, they already would. Because it's like, it's literally, if you look at the ratios, it's disgusting. It's like 1 to trillions. So you've got one of these and trillions of these, and as a result, adding, a trillion, 1 million, doesn't make it more likely for these to break apart, because if they could, they already would have. So these equilibria are so out of balance that the water doesn't really become a player in the game. You'll see that when we start iceboxing these, we actually will just exclude the water, because we understand that there's so much of it there that it just doesn't matter at some point. Is that okay? That's an interest. I've never thought about that in terms of Le Chatelier's principle. That's really cool. Guys, what else? Other questions? You guys good? Okay. So guys, with that said, you guys already have the notes, right? Oh, man. I make this too easy for you guys. Guys, can you agree with all of this? You're going, I don't know. I don't know what it says. So, guys, this is what we're saying. If you have a strong acid, this is why I had you define in your little noodle strong. Strong means busts apart, ionizes completely in water. So guys, the strong acids completely transfer their protons to water. And these are the 7 that do this. And that means that their conjugate, oh look, we can underline them. Guys, that means that all of these conjugate bases are of negligible strength. Yeah? Then guys, what about the weak acids? Well, they partly ionize in water, and that means that their conjugate bases actually function as bases. But guys, the new idea that you need to get sort of comfortable with right now is there are shades to this. And that's what this is talking about. So let me zoom into this. I know that yours is itty bitty small. But guys, above this line should be our 7 strong acids. Not just those 3. It should be all 7 of them. But then, guys, you'll notice in the right-hand column, we've got their conjugate bases. So you could say conjugate base to this if you want. But the idea, guys, hey, there's our word negligible, or the more illustrative term, worthless. So guys, all of these strong acids have worthless conjugate bases. But then guys, we have degrees of not worthlessness. So H2SO4, the bisulfate ion, guys, that is actually acidic. It can give away a hydrogen ion, and when it does, it turns into sulfate. Guys, this is a relatively strong weak acid. It does reach equilibrium. Its conjugate base does actually function as a base. Not very well, but it does function as a base. Then, guys, when we get all the way down here to the biphosphate ion, guys, this is still acidic. It gives away hydrogens a little bit, but phosphate is a pretty good base. And so the phosphate ion is actually able to take some of those, quite a few of these hydrogens back. So guys, it does still reach equilibrium. So all of these are reaching equilibrium. That was meant to be equilibrium the whole way through that section. But the idea is the stronger the weak acid, the weaker the conjugate base. But if you understand the idea that the conjugate base is actually what defines the strength of the acid, because the better this is at pulling in hydrogens, the more that it will drive the reaction in the reverse, causing this to form, making the acid weaker because less of it breaks apart. Because that was a really big idea. Again, I'm going to get in big, deep breath position. Guys, what do you need to talk about relative to this? Yep.
The conjugate bases of the strong bases, like the acids are those.
Are you talking at the bottom of the table? Yeah, good. Yes. So hydroxide is a worthless acid. It does not give away hydrogen. H2, weird thought, worthless acid. Bunsen burner gas, worthless acid. These don't give away hydrogens. But their conjugate bases take in hydrogens like crazy. Yeah. So we don't really talk about, kind of. We talk about the idea that OH is sort of the foundation of our strong bases. Technically, hydride ion and the methyl group, CH3, are both also strong bases, but you won't get into those ideas until you get into organic. So for our purposes, the only thing that we need to keep track of as a strong base is OH, because it's present in our strong bases. There are other things. Frankly, you won't. So you know how we said Arrhenius, Bronsted, Lowry? There's a third definition for acids and bases called the Lewis definition. Lewis dot structures, electrons, but you won't get into that until AP. Or until college. Sorry, I know, my bad. Until college. I was thinking, should we just do it now?
Yes.
There will probably be a couple multiple choice questions on the AP test about Lewis. We normally do it during review. Can we just do it now really quickly? Is that okay? Yeah, let's just do it now. So guys, are your notes printed single-sided? Or are they double?
They're single.
Single? Find a back to write on. Wasn't planning on doing this, but write it down. Bless you. So, guys, identify your acids, your bases, and your conjugates. Got it? So what is NH3? Acid or base? Base. So I'm going to just scratch this down. This is our base. This is our acid. This is our conjugate acid. And this is our conjugate base. Is that okay? Okay. There was a point that I wanted to make there that was sort of related. Acid, base. Oh, why don't we just do this right now? Guys, please don't write this down, but okay. Guys, can you just look at the bottom? We've already done this today, right? In the bottom equation, what's water, the acid or the base? Base. Which one is it? So is water a base or is water an acid? Yes. What do we call that? Do you remember?
No, it's something.
Do you know? Amphoteric.
I said ambidextrous.
Let's go with that. It's ambidextrous. Well, it's the same root word, right? It swings with both hands. So guys, if you page back in your notes, you know what? Don't. We'll get it in. There's a slide on that in just a minute, but we just covered it, so we're good.
Other things that are amphoteric?
Absolutely. Yeah, like so for example, the HSO4 ion, do you guys know about bi? That this is sulfate, but when you add a hydrogen to it, it becomes bisulfate. The bisulfate ion actually can do both. It can go as an acid and form sulfate, or I'll just do this, or it can go it can do both. It doesn't. It has the well, it could, depending on what it's with. If it's with water, it'll do this. But if you were to put this with an acid, it would function as the base. Yeah, so actually it's interesting. All right. We're going down so many rabbit trails.
Yeah.
Sodium bisulfate is actually the salt that you use to control the pH in a hot tub. The reason is because when it dissolves in water, you get sodium and you get bisulfate. And that falls apart completely. It's a strong electrolyte. So what you're doing is you're adding bisulfate ion to the water, and then that actually can muck with pH in order to balance the pH of your hot tub. Yeah, anyway. I'm convinced you shouldn't own a hot tub if you don't have a degree in chemistry. All right, so guys, back to this. Acids, bases, and conjugates. I'm just going to erase. I'm going to get rid of this. It was either that or I had to rewrite the whole top thing.
Is there like a bigger like ratio?
Yeah, maybe. So, guys, this then becomes the point. How does this work? And guys, this is important in a bigger sense, in addition to what we're just doing now. Easy there. Actually, I want to rewrite that. Oh. Not boring to me. Just for illustrative purposes. Okay, so guys, the question becomes, there we go. The question becomes this: how does this chemistry happen? How does NH3, which has a full octet, how does NH3 form a fourth covalent bond with a proton, with a hydrogen, in order to turn into NH4? We touched on this a little bit last time. But guys, what happens is this proton, this hydrogen nuclei from the water actually globs on to these electrons right here. Guys, that's how this happens. Now, guys, think deeply with me here. When we think Bronsted-Lowry acids and bases, what do Bronsted-Lowry bases do? What do Bronsted-Lowry bases do? They accept protons. What do Bronsted-Lowry acids do? They give protons. Now, guys, here's what I want you to do. Change your focus. You are looking at protons, and that makes the water the proton giver and the ammonia, the NH3, the proton taker. Now change your focus to the electrons. When we look at the electrons, what NH3 is doing is actually donating electrons to this proton, allowing them to bond together. Does that make sense? Is that okay? Now, guys, what we're now talking about are what are called Lewis acids and bases. And yes, it's the same Lewis that was fixated on electrons, who did Lewis dot structures for atoms, who did Lewis dot structures for molecules. Lewis, in his research, was trying to understand the world through electrons. And so when Lewis started thinking about acids and bases, he said, Bronsted-Lowry, you're right. Acids give away protons and bases take them in. But if we shift our focus to the electrons, then the bases actually donate electrons and the acids take them in. So in the Bronsted-Lowry sense, this is an electron donor and this is an electron acceptor. Not the O, the proton. So in this sense, your base, your electron donor is the NH3. Your acid, the electron acceptor, is the proton. Yeah. So now you're going, crap, how am I supposed to keep track of this? Well, guys, when you get into organic, oh yeah, like a child. Just a second. Is it further back? Oh, no. Sorry, guys, just a second. There we go. So, guys, in organic, what you learn to do are what are called electron pushing diagrams. You see these little red arrows? Those little red arrows represent my blue arrows on the board. When you think about organic chemistry, guys, your acids and bases are all understood through the Lewis context, and that's one of the things that makes this class so evil, is you've got to track electrons through all of these reactions. They're called electron pushing diagrams. So guys, this is an example of an electron pushing diagram as the electrons are being donated by the NH3 and accepted by the proton. How are you supposed to keep these straight? Guys, maybe 2 multiple choice questions on the test, but here's what I do. I forget about Lewis acids and bases, and I think Bronsted-Lowry. So guys, watch my hands. Bronsted-Lowry says acids give away positives. So if you're giving away positives, what are you doing with negatives? Taking them in. It's the opposite. If the charge is opposite, the direction is opposite. So if acids give away positives, they take in negatives. If bases take in positives, they give away negatives. It's really the inverse of Bronsted-Lowry. So if you understand Bronsted-Lowry, you understand Lewis. Just understand opposite charges, opposite directions. You guys are going to thank me for this when you get to college, and they'll cover this in 12 seconds. And then they just start doing Lewis electron pushing. Because if you can just remember, electrons are the opposite charge, so the direction is opposite as well. It's going to save your butt. You okay? Okay, so guys, one more thing really quickly, and then we're going to get back into this. Please remember this. You're going to see things on the test, even in homework today, that says, is this a strong or weak acid or base? Guys, let's go through this in our head. What are the strong acids? The big 7. What are the strong bases? The OHs of group 1 and heavy group 2. Which are the weak acids? The ones that aren't strong. Right? But then, guys, what are the weak bases? Here's the answer. For AP, nitrogen. Guys, compounds that contain nitrogen are weak bases. That's what you need to know for this class. If you see nitrogen in a compound, and it's not just NH3, if you see any compound that has a nitrogen in it, you're going, that's a strong or a weak base. Yeah. That's a weak base. Man, that was a whole lot of stuff, y'all.
They're always.
Well, so if the question is strong or weak, acid or base, yes. Yep. You guys okay? Can we get back into our slides? All right. What's that? Do them in your head. Imaginary. Okay, so guys, are we good with all of this? All right. Oops, drawing dots. So now, guys, conjugates. Are we good? Acids and bases and conjugates? I don't want to slow down. Michael, you good? Good? Okay, what about amphoteric? Good? Good. All right. Now, guys, this is going to get crazy. The auto-ionization of water. Guys, did you like my analogy of water being a playground? Do you remember that? The idea being that when you're a kid on a playground, you play on the playground, but you don't play with the playground. And guys, up until now, that's been our understanding of water. Aqueous chemistry happens in water, but water is not a part of what's happening. Guys, now we need to talk about why in acid-base chemistry is water no longer just a casual context, like the playground, it actually gets involved in the chemistry. Guys, really quickly, grab your AP equation sheets. All right. So guys, this is about to go somewhere interesting. This is a big thought. Is water an acid or is water a base?
Yes.
Yeah. So guess what? Not only is it amphoteric towards other substances, it's amphoteric towards itself.
Why are we not all dead?
What's that?
Why are we just not all dead?
Well, there's lots of reasons.
Alive.
So guys, the idea is this. Water molecules. We've got a cup of water. And guys, these water molecules, for the most part, are stuck together as water molecules. But if we were to look at that. Okay. So guys, water molecules, and for the most part, they're like this. But remember, these are amphoteric. And so at any given moment, these can actually function as acids towards a neighbor or as a base towards a neighbor. So guys, say for example that this water molecule, just because of randomness, functions as a base. Well, what's it going to do? Well, it's going to take in a hydrogen. And when it does, we're going to end up with this, hydronium, and we're going to end up with this, OH. Did I give this to you? Oh, man, I did. So, guys, this is the balanced equation that represents this process. Write the KC expression for it, y'all. Don't look at the next slide. Write the KC expression. I didn't give it to you there, did I? Oh, good. Guys, write the KC expression. Promise me you're not you're looking, aren't you? Liar pants. If it were up to you guys, you would have eaten the apple.
Oh my gosh.
So guys, as you're doing this, I'm going to freeze this for a moment. I lost my copy of the slides, so we're on slide 7. So 7 through 13. I want a copy of these because I'm not exactly sure how the transitions proceed, but I know where I want to get you. So I'm just going to print these off really quick. Uh-oh. I think I may have printed the backgrounds. All right, so guys, did you get your KW written out, or your KC, PS, KW? So guys, it goes like this. If you didn't get this down, we've got KC is equal to products, which is H3O plus and OH minus. And then in the denominator, does anybody have any heartache over me just doing that? Is that okay? Water times water is water squared. Is that okay? But now, guys, we've got a problem. And if you look down, you already know the answer. But if you didn't look down, can you reason through why this is wrong? Water does not have a molarity. Guys, this is a pure liquid, and consequently, it does not belong in the expression. Guys, this then leads us to this expression. Guys, that leads us to this. But you'll notice that we change the C to a W. This is called the KW expression, the water equilibrium expression. Now guys, please don't read ahead, but guys, let me explain this to you. Maybe I shouldn't have given you the slides, because this lands better if you haven't read it first. But guys, here's the idea. We understand that, where'd my OH go? Over here. Guys, we understand that a very, very, very little bit of water does this. If we have a cup, oh, that's gross. If we have a cup of water, guys, almost all of the water is still water. A very small amount of it does this. But guys, we can measure the molarity of hydronium ion and hydroxide ion in the water. Now guys, here's the interesting point. If we can measure the concentration of this and the concentration of this, what will they be compared to each other? The same. Because guys, every water that goes through this process, you get out of hydronium and you get out of hydroxide. Now guys, the thing that's interesting, and you can write this down with me if you want, guys, we actually know what that value is. It's 1 times 10 to the negative 7th molar, but this is also 1 times 10 to the 7th molar. At room temperature, the molarity of both the hydronium and the hydroxide ion are 1 times 10 to the negative 7th. Guys, you ready for the aha moment? That's why the pH of water is 7. That's why the pH of water is 7. You may remember that pH is equal to the negative log of hydronium ion concentration is equal to the negative log of 1 times 10 to the negative 7th. And guys, that's 7. That's why the pH of water at room temperature is 7. But now guys, let's do this math. If this is 1 times 10 to the negative 7th, and if this is 1 times 10 to the negative 7th, when we multiply those together, what do we get? 1 times 10 to the negative. Find it on your AP equation sheet. Do you see it there? Just a second. I need to find it first. So guys, it's on the equilibrium side on page 3. It's about halfway down that cell, if you will. KW is equal to H times OH is equal to 1 times 10 to the negative 14th. So Jared, before we ask your question, guys, how is mine different from the AP sheet, and why doesn't it matter? So guys, if you look at mine, I've got hydronium ion rather than hydrogen ion. Do you remember the idea?
Yeah.
Guys, when we talk about acid-base chemistry, we can choose or not choose to include water. And so guys, if we don't include the water, we just end up with this. We end up with hydrogens and we end up with hydroxides. But guys, please be clear on this. This doesn't exist in water. It can't exist in water. So where do those hydrogens actually go? To water to form hydronium. Sometimes it's easier for us just not to include it, and we don't. But guys, we understand on the AP sheet, if this says hydrogen plus, it's really hydronium ion. We just don't represent it that way. Jared, you had a question?
pH plus QH equals 14.
Maybe, because you understand logarithms better than I do. Yeah, we're about to go there. Yeah, right. So, but guys, right now we need to talk about this. I don't think I included this in your notes. Oh, I hate it when it does this. Now I have to staple it because it printed double-sided. Okay, so guys, we've done this. We've done this. We're going to stay here. Okay. So guys, this is worth doing. This is worth doing in your notes. So guys, what is the value of kW? 1 times 10 to the negative 14th. Guys, that is a constant. Think about this with me. Remember when we did the flippy tubes? Yeah, flippy tubes? And it came to 70-30? Was that right? 70-30? And it didn't matter what we did. That K value is constant, right? Can we change it? Yeah, we can change the temperature. But guys, that K value is constant. Yes? Please agree with me, yes? K doesn't change. Neither does this. Guys, this value, did I bring the value in the slide? Does it come up? It doesn't, does it? I'm going to write it in. So, guys, this value, 1 times 10 to the negative 14th, if we don't change the temperature, we don't change the value. Does that make sense? Here's what that means, guys. This becomes a teeter-totter. It's worth writing down. Guys, this thing becomes a fulcrum. You notice I said the word seesaw in the notes. So guys, the idea is this. When we have a solution of water, we've got some hydrogen ion, and the amount of hydrogen ion is equal to the amount of hydroxide ion, 10 to the negative 7th molar. But guys, this then is what this allows us to do. Imagine that we've got our bucket of water and we dump hydrochloric acid into this. Is it okay if I say the chloride is a spectator? Is that okay? Yeah? So guys, if we dump hydrochloric acid in this, functionally what we're doing is we are bombarding this solution with hydrogen ions. So guys, what's going to happen to the amount of hydrogen ion? It's going to go through the roof. But guys, that causes hydroxide ion to drop in an equal but opposite amount. So guys, in pure water, hydrogen and hydroxide are balanced at 1 times 10 to the negative 7th molar. But if you dump in a bunch of acid, a bunch of protons, hydrogen ion goes up, hydroxide ion goes down by the same amount. So why is that important? And guys, the answer is this. If we ever know the hydrogen ion concentration of an acid, we can figure out the hydroxide ion concentration of the acid by using this as a constant. Does that make sense? Is that okay? Okay. So guys, with that idea in mind, let's now take this idea and ask ourselves, how do we measure these concentrations? How do we know how much hydrogen and hydroxide ion there is? And guys, the answer is pH. Again, this is in your notes. It is, right? So guys, how do we know how much of each? And guys, the answer is pH. But you'll notice I wrote it in both forms. Which one's on the equation sheet? Is it H or H3O? Just H. They don't give us the H3O. So guys, we've got pH is equal to the negative log of hydrogen ion. Ooh, look what's next to it. POH. So guys, if pH is the negative log of the concentration of hydrogen ion, then POH is the negative log of the hydroxide ion concentration. And Jared, that's where your brain went, and we're going to wrap up by going there. But guys, just by way of review, remember that pH is a mathematical expression that tells us the strength of the acid. The lower the pH, the stronger the acid. And guys, so low pHs are acidic, higher pHs are basic, and it allows us to figure out it allows us to quantify the concentration of acids. Is that okay? So guys, that brings us to this, which is actually where we're going to stop today. I wish I had a version of this where the acids were on top, but I guess it sort of makes sense. What would be a good color to write on against this? I want something that stands out. Like yellow? Yeah, that's gross enough that it works. Then guys, I want a thinner pen, and let's talk. Okay, so I can write. Here we go. So guys, let's start all the way at the very, very bottom. Actually, no. Let's do this. Before we do, let me just give you a moment to sort of look this over. I think you're going to find many of the connections without me. Guys, left to right, top to bottom.
Should have sweat.
What's that?
Should have added sweat. Should have sweat.
Ah. So, guy, yeah.
Like most of the things listed as acidic are things that we eat or drink.
Right.
And,
Yeah.
And most of the things that we cannot eat is because they're bases.
And there's soaps, ammonia, bleach, borax. But yeah. Guys, let's do this. What do you notice about, oh, I don't want to put equals. That's bad. So guys, what do you notice about these? And I would encourage you to write these down. Guys, what do you notice about these two columns? So when one of these gets bigger, right, less negative, when one of these gets bigger, the other one gets smaller. But guys, in all cases, when you take this and multiply it by that, what do you get? 1 times 10 to the negative 14th. So guys, this is your KW expression. Hydrogen ion concentration times hydroxide ion concentration is KW. So guys, multiplying these together will always give you 1 times 10 to the negative 14th. So guys, let's do this. For example, stomach acid is HCl. Is that too small? Can you see that okay? Is it okay? What color would be better? Green? Okay. Yeah, that's not really jiving, is it? Yeah, that's true. Okay, so let me go. Oh, I still want to zoom in though. Okay, so H. Is that any better? Okay, so guys, let's say that your stomach acid is 1 molar hydrochloric acid. It's actually really close. It's a little above that. And is this okay? A little bit above 1 because this is pH. A little bit above 1 means a little less acidic than 1 molar. Is that okay? Okay. So guys, literally your stomach is a bag of, let's call it 1 molar hydrochloric acid. So we know the molarity, we know the molarity. The molarity is 1 times 10 to the negative first. That's hydrogen ion concentration. But guys, look at how low the concentration of the hydroxide ion is. This is a lot. This is 0.1 molar. So guys, the hydrogen ion concentration is 0.1 molar. The hydroxide ion concentration is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1 molar. Guys, that's the molarity of hydroxide ion concentration. This is the molarity of hydrogen ion concentration in 1 molar HCl. Yeah. Okay.
And 1 pH.
Yeah.
Does that mean if you had a hydrochloric acid solution with like 10 molarity?
It'd be pH 0.
It'd be pH 0, not negative 1.
Correct. Yeah, pH negative 1 would actually be a, wait a second. So 1 molar, 10 molar would be -1, right?
Yeah.
1 molar would be 10 to the 0 is 1, right? Yeah, so 1 molar would be pH 0. Yeah, right. So this would be, yeah, right, because 0.1 molar is 1, pH 1, so 1 molar would be pH 0. And then 10 molar would be pH -1. Yep, you got it. Is that okay? Now, guys, go all the way to the other end of this. Let's just say we've got, well, sodium hydroxide, which is 0.1 molar. We've used that in lab. Guys, now the concentration of hydroxide ion is 0.1 molar, and now the concentration of hydrogen ion is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1. So guys, what you should be able to see is that they trend opposite. As the concentration of hydrogen ion gets bigger, the concentration of hydronium ion gets smaller. So our strong acids have got a bunch of hydrogen ion, not much did I say hydronium? Hydroxide ion. And then guys, in our bases, we don't have much hydrogen ion, but we've got a lot of hydroxide ion. But guys, these always trend relative to this idea that their product multiplied together is always 1 times 10 to the -14th. Is that okay? Now guys, this. Let me zoom out and clean up my mess. Are you really okay with those ideas? Okay, so now let's do this. Going back here, and I'm going to make my pen a little bigger because this will stand out pretty quickly. Now guys, this. Are you comfortable with the connection between pH and hydrogen ion concentration? So pH is equal to the negative log of hydrogen ion concentration. And then similarly, guys, we can go pOH is equal to the negative log of hydroxide ion concentration. Is that okay? Now this. What do you notice about this column and this column? But just looking at those two, as you go down the columns, they always add up to 14. Jared, that's what you were talking about. Guys, this is an important idea. When we have acid-base systems, their pH and their pOH always add up to 14. Find that on your AP equation sheet. There you go. Do you see it there? You guys okay? Yeah? Okay. So guys, that then means we can do this. Taking this to the horizon, guys, we are now comfortable with these relationships between hydrogen and hydroxide. Always, the product of that is always 10 to the -14th. We're comfortable with the idea that going from hydrogen ion to pH is negative log of hydrogen ion. From going to OH concentration to pOH is the negative log of hydroxide ion concentration. And then pH plus pOH always adds up to 14. Are you good? Yeah? Okay. So guys, that means then that this makes sense. pH plus pOH is 14. And then guys, finally this. And we're done. Guys, last thing we need to talk about. When we talk about strong acid, you know what, rather than reading the words, let me show you. When we talk about strong acids and bases, guys, I would encourage you to draw this with me. Time to draw, ooh, bad color. Time to draw a beaker. All right, it's going to be green because I can't change. Guys, time to draw a beaker. Put some water in your beaker. What is the hydrogen ion concentration in this beaker at room temperature? 1 times 10 to the -7th molar. I'm going to write it out. 0.1, 2, 3, 4. I want to move it down. It'll be more fun. Oh, you're okay. So point 1, 2, 3, 4, 5, 6, 1 molar. And that's hydrogen ion. I'll write it in just to be clear. That's hydrogen ion. You okay? Now guys, here's what we're going to do. We are going to dump in, technically bubble in. We're going to bubble into this a pant load of HCl. How much did we decide that is? It's related to butt tons, right?
Less than a crap ton.
Crap tons. Okay. So now let's give this some numbers. Let's say this is 1 liter. And let's say this is 1 mole. Thanks. I made them up just for you. Now, guys, we know this. Molarity is equal to moles divided by liters. So what is now the molarity of this, what is the concentration of hydrogen ion in this solution? Well, it's 1.1234561 molar of hydrogen ion. So it's 1 molar because we put 1 mole into 1 liter. But it's 0.0001 because there was a little bit of it there to begin with from the autoionization of water. So guys, here's what we do with this. We call it 1. When we're figuring out the concentration of acids and bases, we disregard the little bit of hydrogen or hydroxide ion that is present from the autoionization of the water. We just call this 1 molar. Is that comfortable? Do you see that? So guys, with the understanding my board's going to freak, that is what all of this means. In the case of strong acids, we consider the concentration of the acid to be equal to the concentration of hydronium ion created from the addition of the strong acid. Why is this appropriate? Because the concentration of the hydronium ion that's there from the autoionization of water is so stinking small it's a rounding error. So we just don't include it. So guys, the bottom line is this. Let's just do this together to wrap up. Let's use John numbers. 1. So guys, we have 1 molar HCl. What is the pH? 0. So guys, the idea is this. If it's 1 molar HCl, we're going to call that the same as 1 molar hydrogen ion concentration. Technically, it's not, because we've got a little bit of hydrogen ion from the water breaking itself apart. We call it 1. So then we go pH is equal to the negative log of hydrogen ion is equal to the negative log of 1 is equal to 0. Good? Is that okay? Me either. Just pretend. Yeah, just pretend. Or use your calculator or talk to... See, Clara, another reason why you don't want to teach math. It's abusive.
There you go. But this is what makes sense to us, though.
I know, which is why you should teach chemistry. Because now math means something. See how... Guys, here, okay, so... Let's pretend like Clara's not here for a minute. You don't know this, but my year-long goal has been to get her to change her major to chem ed instead of math ed. Anything you guys can do to support me in the effort?
Chemistry, you can do like hands-on labs. That's the chemistry actually makes sense. I touch everything.
Right, that's right. Hey, so guys, 2 more seconds. Foreshadowing. Little bit of foreshadowing. Is this idea okay? Okay, then this and we're done. Won't let me do it. Hold on. Does that feel like a lifetime ago we drew that? So guys, last thought. Nope. Guys, don't miss this. 1 molar acetic acid. Its pH is not 0. 1 molar acetic acid's pH is not 0. Remember when we had 1 molar HCl, we said that that was 1 molar hydrogen ion, pH is equal to. But guys, here if we've got 1 molar acetic acid, that is not equal to 1 molar hydrogen ion concentration. Why not? It's a weak acid. So what could we do to figure out the pH of a weak acid? Icebox. That's what we're doing Thursday. So now, again, continuing this effort to get Claire to not teach math, I know that you're dreading this. See, I'm kind of overdoing this. Because you know that you're going to have to use the quadratic formula. And we hate the quadratic, right?
Yeah.
Yes. You catching this? Yes. Actually, guys, it's really cool. When we talk on Thursday, there's one really interesting contextual assumption that we can make, and we don't have to use the quadratic formula. When you see it, you're going to be like, okay, that's cool. We'll talk on Thursday. So, guys, we're done. Homework. Okay, you ready? Guys, all of you, big deep breath. Big deep breath. No!